Good morning, Kelk. Usually every year, this lesson's typically started with, but I'm calling this Intro to Calc number 5 this year. It is the first note sheet that you skipped. It is called the instantaneous rate of change. It's the door problem if you look at it. We're going to use this for number 5, and I'll have number 5 is a swimming. I think it's the diver or swimming pool or whatever. I don't know. It's something like it. It kind of comes together with this one for the assignment. So in calculus, we talk about instantaneous rates of change. If you would not have been isolated last year, you would have talked about that in pre-calc last year, and you didn't. So my job is to try to hitch really quick in a lesson, and we'll dive a little deeper into it later. We are going to hook what you learned the average rate of change was in Algebra 2, we called it the Aroc, and how that applies to the instantaneous rate of change in calculus. Okay, so what we're going to do is this whole problem banks off of the door problem. So in the diagram above, shows a door with an automatic closer. At time t equals 0, someone pushes the door open, okay, it swings open, and then it slows down and it stops, then starts closing. Just picture yourself walking through a door with a door closer coming into school. It closes slowly until it hits a certain point when at t equals 7 it slams shut. As the door is in motion, the number of degrees, okay, d, it is from its closed position depends on time. So what I want you to do is I want you to think about this for a second. If you have to pause it, pause and think about it for a second. I want you to make a reasonable graph that you think if you had the function, what would this graph look like if you graphed it, okay? And I don't know if anybody will get it right, but I'm going to say t equals, I don't need to put t equals there. I know I'm going to start at 0, okay? I start at 0, and I know somewhere down here at 7, okay, the door will be closed. I will be back, okay? So I know somewhere I'm starting the door is shut, I open it, it swings open, it closes, or it swings open, it stops opening, and then it starts slowly closing. Think of a door closure on an automatic door, okay? And now remember, this is time on the bottom. It's time in seconds. And D is degrees. Door is open, okay? So I picture myself walking through those automatic doors. You usually give it a pretty good jack, and it usually opens quickly, and then it typically starts closing slowly, and stops. That's my reasonable graph. It doesn't open and close at the same rate. When you push that door open, it opens quick. It finally stops opening somewhere, and then that door closure, it starts to go, and then the closer it gets to shutting, it slows down even more so it doesn't slam all the time, okay? So just think about that. Hopefully that makes a little bit of sense. And then this is in degrees that the door is open. So what we're going to do is suppose d is a function of t. Suppose we had an equation to model this. And the equation we're going to use to model it is d of t equals 200t times 2 raised to the negative t power. What I want you to do is hit pause. I want you to graph this little bugger in your calculator, and we are going to go from there. So I'm going to pull up my graph. I'm going to add a graph. And okay, we can't put t in the calculator. You guys know this. This is f of x. I need to convert all my variables t in my equation. I need to convert them into x's because your calculator only graphs x and y coordinates. So I have 200 x And now if I enter it like it's given, I would actually have to hit the multiplication sign before I hit that parenthesis, because you can't hitch a variable next to a set of parentheses without the designated operator there. So I'm going to say that, and then I'm going to say it's 2, and I need to raise my 2 to the negative x power, and I'm going to come down, I'm going to close my parenthesis. So I've entered it in. If this little guy right here, if that multiplication symbol is not in there, I do not believe it's going to graph for you, and you're going to pull your hair out and say, Kruger, I want to graph, because you're missing the stupid little dot. I'm going to hit enter. Great. Now I need to think about seeing a decent viewing window. We need to organize this into a viewing window. Don't guess, okay? Don't just sit back and guess. Think about it a second. We're going to go to menu. We're going to do our window zoom. We're going to do our window settings. I am a guy that likes to see his X and Y axis. Think about this. The door opens and it's completely shut in 7 seconds. My X axis is time. So I'm going to go from before time, -1, till about 10 seconds, because I should be able to see my graph then. And I'm going to make my X scale in 1 because I only have 11 units on there. And now think about this. How wide, what's the most a door can open? Well, think about it. You have a knob on there. If you opened it all the way, depending if there's a wall there or not, a door should be able to open minimally 90 degrees, but they can go past 90 degrees. Think about these doors. If it's not going to hit a wall, if it can open all the way. So I'm going to go, because I know down here my maximum is going to be somewhere, I don't know, you can put 150. I'm going to go with 120 degrees because my Y scale is going to be so big. I think I want to put about -10 to see my axis. And if I go -10 to 120, I don't want my scale to auto generate for me. I don't want it to be in ones. I'm going to go, every tick mark is going to be 10, and I'm going to hit OK, and there's my graph. Okay, it's a beautiful little graph. Well, Kruger, it's supposed to be at 1, 2, 3, 4, 5, 6, 7. Why is it not closed at 7? Well, you remember when you did regression, okay? This model approximately is going to represent the door closure, okay? And I need lots of numbers here because it's in degrees, okay? Now, what I want you to do, and I'm going to come back here. Let's see, I'm going to close this little guy. And now, so there we have the graph. I already pasted it in there. So what I want you to do is I want you to complete this table quick. You're going to hit pause. I'm going to show you how to do it, and I want you to really do this. Knowing how to operate your calculator is a big deal in here, okay? I want you to make a table of values for D, the degrees it's open, for each second from 0 seconds through 10 seconds. I understand we said it's closed at 7 seconds, but we're using our model graph here. And make sure anytime you're going to do it, you're going to round your answers to the nearest 3 decimal places. Here's the easiest way to get all these numbers. Go back into your graph, go menu, don't analyze, go trace graph. Type in the numbers we want. We wanted 0 degrees, right? That was our first one. I can read my ordered pair, so I'm at 0, 0. If I'm at 1 second, how many degrees open? Ooh, it's 100 degrees open. If I'm at 2 seconds, and I just keep typing these numbers physically in and hitting enter, now I'm at 100. Then when I go to 3 seconds, okay, I'm not using the arrow to go back and forth. I'm physically typing the number into the calculator. So I really want you to hit pause. I want you to fill all the rest of these out, 0 through 10 seconds. Make sure you can do it. It's a good little operator on using your calculator. I'm going to escape out of there, and I'll be back here in a second. Hopefully you did hit pause, and pause is gone now. And I'm just going to represent here. These are all the values I got. You should have gotten the same, I believe, rounded to the nearest 3 decimal places. I didn't hit decimals till I got down here, roughly at 5 seconds. At 5 seconds, it was 31.25 degrees away from closing. 18.75 away from closing, and I came all the way out to 10. Okay, we're going to use this here in a minute now. So now I got to go to my next screen, and what we're going to do is we're going to use the graph. Okay, and a big part of calculus is reading a graph, interpreting the graphs, lots of different pieces and parts. So, question to you is, at time t equals 1 second, does the door appear to be opening or closing? Well, I got to find where the heck is 1 second. So I'm just going to come to my graph 1 second. I'm going to come straight up. Oh, there's about 1 second. That's a really crooked line, but it's close. Does the door appear to be opening or closing? Well, I would say the door is opening. Why would I say the door is opening? Here's a huge part of math, huge part of calculus. Explain it. I am going to say the door is still opening because I can see on here my function is increasing. My function, it's still going up. And for this model of the problem, I started at 0. I pushed the door open, so it's going open, 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 open. Okay, it keeps going up. Well, how about at time t equals 3 seconds? Does the door seem to be opening or closing? So I'm going to come down here at 1, 2. Here's my t equals 3 seconds. I'm going to track that little rascal up there, and I'm right here. Well, what does it look like it's doing? It looks to me like it is closing. And I say it's closing because my function now is decreasing. Okay? You can read that graph. This is degrees open, and this is seconds across the bottom. Okay? So I've explained it. Is there a time t? Is there a magical time when you push that door open that when the door is not opening nor is it closing? Well, obviously there is, because the door is not going to constantly be swinging. If so, what is that time? Well, hopefully it's pretty obvious that that time is somewhere right there at that maximum. It's opened its maximum point right there. How do we find that? We come back, we grab our calculator, we go Menu, Analyze, Maximum, bada bing, bada boom. What is the time at which the door stops closing? 3 decimals, 1.443 seconds. Okay? So I'm going to say, yes, it does appear it stops at t equals 44, right? 1.443 seconds. If so, explain your reasoning. Well, there's a change from increasing to decreasing. Increasing is open in this application. Decreasing is close. So if there's a change from opening to closing, it must have stopped. It has to stop somewhere. Right there, obviously, my rate of change is 0. Okay, well, what do you mean rate of change? Well, we're going to get to that here in a second. Before I get to that, I need you to think back a couple years, guys. Okay, I get it. Remember back to how we found the average rate of change. We did this in Algebra 2. You probably didn't even do it in pre-calc last year because you would have done it more towards the end of the year. You might not remember it all, but do remember we called that little bugger the Aroc. Okay? The Aroc, the average rate of change. In calculus, what we do is we convert, and we don't talk as much about the average rate of change anymore. We convert that into what is called the Iroc, the instantaneous rate of change at a particular moment in time. And we have to have calculus to find the instantaneous rate of change, okay? That's a big deal in calculus. It's one of the main operations we'll learn how to do. So what I did here is I tried to make a little graph. And what we did when we did this, okay, we had a curve. And in Algebra 2, what we did is we found 2 points on that curve, okay? I got this little point right here, which is the point x1, comma, y1. And we have this point up here, x2, comma, y2. Well, think about it. If this is time, and this is degrees open, if I need to find an average rate of change over time, okay, what is average rate of change? Well, wouldn't it be the slope? It's just putting it into the slope, the change in y over the change in x. So what that would do is that gives me my change in degrees over my change in time. Okay, when I divide so many degrees by so much time, that gives me average degrees, right? And it averages them all over time, okay? We're going to use our calculator to do most of these, but what it did was, when I do that, what does it do? Technically speaking, we're finding the slope of that pink line, okay? Well, that's average rate of change. What I need to do in calculus is, let's come on here and let's say, hey, I want to know what my instantaneous rate of change is right there at that point, because obviously the rate of change here is going to be different than it is across that line. It's going to be close, but how about here? I need to be able to find all these different instantaneous rates of change right there. And we're going to do that. I'm not going to really hit it too hard, but the way you do that in calculus is we make this time interval right here, we make this time interval so small that it becomes an instantaneous moment of time. And you'll see that later on in this lesson. So we let time approach zero. My change in time approaches zero. And when I do that, that converts me into instantaneous rate of change. I don't expect you to fully understand that right now, okay? We'll get there. So that's your little rebuff on an average rate of change, okay? So I'm going to come to my next slide. Find the average rate of change at which the door is moving for the time interval, okay, 1 to 1.1 seconds. Well, let me come back here. Let me get back into some function form, because what is really another way to represent y2? All this y2 is right here. How did we find that value? Oh, we took our function and we put that x value into it, didn't we? So really, this slope modification of a line in calculus kind of turns to f of x2 minus f of x1 all over x2 minus x1. We talk a lot about function form. We get into a lot of technical math notation. This is no more than a y value right there. Okay, so that's how we're going to look at it. So when we come here, how the heck are we going to do that? Well, because this is a time interval, technically speaking, we need to know what the heck is f of 1 so we can get a point 1 comma something, right? We need to know what is f of 1.1 so we can say the time interval is 1.1 comma where is the door. We're going to let our calculator do most of this for us, okay? And so what I want you to do, and it's really kind of nice, okay? What we're looking here, we are looking for the change in degrees over the change in time. My change of degrees are going to be f of 1, f of 1.1, okay? So really what we're doing is we are taking f of 1.1 minus f of 1 divided by 1.1 minus 1. That's going to approximately equal my Aroc. I'm going to let my calculator do that. Let me Turn that little bugger off. Let me get my calculator back, and it's really easy to do, guys. Let the calculator do your thinking. So what we're going to do here, we're not going to pull them all off of here. That's too much work. We're going to open, we're going to control, we're going to add a page to our document. We want a calculator page. In here, we want to say menu, okay? Actions, number one, and the action we want to do is we want to define a function. And they're saying define what? Well, we're going to say f of x, because we have to define our function in terms of x. F of x, we're going to say equals, and we are going to define it as we defined back here. And I don't even really have to do this way, but I'm going to show you. I'm going to say 200x times, and then I'm going to put my parenthesis 2, and I'm going to raise this to the power of the negative x power. I'm going to arrow over, I'm going to close, and I'm going to hit it, and it's going to say it's done. Okay, so if I wanted to know what all those table values were in the beginning, I could now come here and say f of, let's say, what was 5? What was f of 5? My calculator is going to go in, it's going to go in, and it's going to grab this function, it's going to plug 5 in for x, and it's going to say 31.25 degrees. If you look at the t-chart we did on the other side of your sheet, that's exactly what it says. So what we're going to do here is we're going to let the power of the calculator do this for us, okay? We just defined our function always to be here, so anytime I hit f of a number, it's going to reach right into here. So watch, I'm going to go Control Divide to get my funky fraction. And I'm going to say, I am looking for f of 1.1, parenthesis, minus f of 1, and on the bottom, okay, I want to take 1.1 minus 1. You can do that mental math in your head, and you can put 0.1 if you want down there, hit enter, it's going to evaluate everything out. Okay, what is it? Rounded to 3 decimal places. My Aroc is basically 26.336 degrees. Okay, I'm going to come back here. I'm going to say, oh, it is 26.336 degrees. That's my average rate of change. That's my average rate of change between, this is a really, really tight interval, between 1.1 and 1.1 seconds. It's 1/10 of a second, okay? That's my average rate of change when the door is there. Based on your answer, does the door seem to be opening or closing at time t equals 1? Well, when I look at the answer, this rate of change popped out. I'm looking at the sign of my answer. Because that's positive, I'm going to say it's opening. And this is a way that we're looking at data or numbers to say whether it was open, because that was a positive, okay? Now what we're going to come down here is we're going to check what we read. What's my average rate at which the door is moving for the time interval 3 to 3.1? Well, all that wants me to do is I'm going to be taking my f of 3.1 minus f of 3, and I'm going to divide that by 3.1 minus 3. Okay? This is going to give it to me. I go right back to my calculator. Please notice this cute little trick. You don't have to retype all that. You can just arrow up, highlight the function you want, hit enter, it will rewrite it for you. Use the side arrow and go in and say 3. Change the 1 to a 3. Go down, delete, that's a 3. And then we want 3.1. It's faster than retyping everything, in my opinion. Everything's in there. I hit enter. Oh, check it out. This is negative 26.899. Okay. Whoa, I got it. I forgot to close that dirty little dog off. So I'm going to do Hopefully I can do it with this. I forget to do that all the time. So now I'm going to come across. No, I don't want. I'm going to keep my pointer on that. And I'm going to come up here. I'm going to grab my pen. And I'm going to say, oh, and I'm going to use the approximately equal to because it's not exactly. I'm going to say negative 26.899 degrees. Okay? Based on your answer, does the door seem to be opening or closing? Well, because I have a negative rate of change, I'm going to have a negative type of slope there. So I'm going to say closing. And I'm saying closing. Why? Because it's negative, function is decreasing. That's how I would see the function's decreasing. It looks like because it's going down, the function has to be decreasing. Okay? Now, here's a big deal, guys. Here's a big deal. Explain why we could not use the same procedure to find the instantaneous rate in which the door is moving exactly explicitly at t equals 1 or t equals 3. It's actually a pretty easy explanation because if I went f of 1 minus f of 1, that would be my instantaneous rate using the same point, 1 minus 1, what I should obviously get is 0 over 0, okay? And I know I don't need to demonstrate this for you, but I'm going to put it up there anyways. And I'm going to come up, and I'm going to say enter, and I'm going to squirrel that across, and I'm going to say f of 1 minus f of 1 over 1 minus 1. Undefined. Why would it say I'm undefined? Well, because I am undefined. What do I get when I'm looking at this thing? Okay, I get 0 in the denominator. It's undefined. Now, let me take a step further just to not beat this like a dead horse yet. I got 0 divided by 0. It is undefined, yes. But that is actually something special we're going to learn here shortly called an indeterminate form. It's an indeterminate form, okay? And that just means because it's an indeterminate form, I can't say anything about it. I'm really unsure what's going on there. I need more information, okay? So what I'm going to do, and that's why I can't do it, because I would be always subtracting the same values in the numerator as I would the denominator, which will always give me 0 over 0. That's not going to work, okay? So what I need to do is I need to figure out a better way for my instantaneous rate. Well, we're going to find an estimate for the instantaneous rate at which the door is moving at t equals 1. And if you notice, what I'm doing here is we are closing this gap. We're making this moment in time from 1 to 1.01 seconds, to 1 to 1.001 seconds, to 1.0001 seconds. We're closing this gap of time, but by closing this gap of time, what is happening when we plug this in, we're taking f of 1.01 minus f of 1 divided by 1.01 minus 1. You can totally see I don't get 0 in the denominator anymore. Hence, it's still going to make a calculation for me. Okay, so I'm going to bring this back up. I'm going to come back up. I'm going to grab that guy. I'm going to squirrel over, and we're going to say 0.01. And then on the bottom, I'm just going to come over and say 0.01. So now I have entered what I wanted. I'm going to hit return, and I'm going to write this down. At 1.01, now, it's a pretty quick moment in time, obviously. But I can see I'm 30.234 degrees open. So let me close this out. and say, get my writing utensil, I am 30.234 degrees. Okay, really small moment in time, even small moment in time, I'm making a closer and closer interval. Well, what happens, what do I do when I take f of 1.001 minus f of 1, and that's going to be divided by 0.01 minus 1. What do I get now? What is this? How does my rate of change from here to here change? It should be getting closer and closer to a moment in time. So I'm going to squirrel over. I'm going to add a 0 there. I'm going to go down. I'm going to add a 0 there. I'm going to hit enter. It didn't change a lot, but check it out. It did change. It did change even in that itty bitty little moment in time. Okay, so we're going to come over, and obviously we're going to do another one. So I'm going to come up and I'm going to grab this, and we're changing that interval to 0.0001. 01. I'm going to hit enter. Notice it may not be a big change here, but I can see these decimals changed. And from this change in time to this change in time, it's not changing as much. Okay, so what we're going to do is we're going to take a little gandy-wandy at these little two numbers here. Okay, and I'm going to put this little guy in here. We had 30.640 degrees. And then this one was 30.681 degrees. Now, I think everybody will agree we don't have any concept of how short of a time interval that is. Okay, 1 second to 2 seconds, but now what would that be? 10th, 100th, thousandth, 1/10,000th of a second. Pretty short. Okay, now what we're going to do to find an estimate at which the 3 seconds is going, okay, how is it? Well, we're going to basically do the exact same thing with our calculator. And we're going to come in there, we're going to type those in. Take a second and type those in. And this one here was negative 26.979 degrees. Yes, you'll have to do this on your summative next week, okay? So this one, every time, remember this is a time interval. Can tell because it's written in interval notation. So if they want me to find an instantaneous rate of change, we're going to estimate, okay? To find an estimate, what we're doing is we're making this moment in time shorter and shorter and shorter, and I can see my numbers hone in fewer and fewer and fewer change, okay? What we're going to do, my guesstimate up here, well, I would say this is going to be something at 30.7. I can see this side's building. I'm not going to worry about the 3 decimal places on a guesstimate right now, but I can see all those numbers are changing. These two are getting a little bit bigger. If I went a little bit farther, that might kick it out, but I don't want to waste too much time doing it. And here, because this is time, I'm thinking f of time, which would be the y, would be degrees at 3.001 seconds minus degrees at 3 seconds divided by the time interval, 3. What does that give me? That gave me negative 26.985 degrees. Now check it out. I'm just making a ballpark here. I can see 26.9, I can see 26.9. Those haven't changed. If I step out one more interval out to this next one ends up being 26.986 degrees, okay? And as I'm going, now I see I have a couple repeating decimals. This one's getting pretty daggone close to where if I had to make an estimate of what it's going to be, if this guy gets much higher, it's going to round up, and come up. You know, if I'm not worried, I could ballpark it at, let's just call it about negative 27 degrees. I'm not worried about all the decimals right now. If I did, actually, no, I wouldn't do that. I would look at this. If I was doing it, I'd look at decimals that didn't change. They may be negative 26.9. And as this guy gets bigger, it might say 9 degrees and I'd round it off. Okay, I'm not going to get too stinking picky on that. Last one, explain how you could use the average rate of change to find the exact value for the instantaneous rate of change. Well, basically what we do, we will not do this all the time, okay? Basically what we do is we let, in the end, our change in time approach zero. But we don't want to do it in this fashion to where things are going over, to where we're doing this and then we're taking 3,3.00001. And then I could keep going, 3.0000001. I could keep going, that's going to change it. Okay, what I'm doing from interval to interval is I'm letting my change in time slowly approach zero. And if there's no change in time, then you have an instantaneous rate right there, okay? So that pretty much sums it up. You have your worksheet to work on there a little bit, and hopefully this made sense. If it didn't, reach out to me sometime today. I think I'll have a little free time this afternoon, and I might be able to hopefully solidify a few questions for you. Other than that, have a great day, and we will talk to you soon.